Well, today we have an anonymous visitor. This gentleman goes by the handle @39Magilla, we found each other because I noticed yesterday. Today is the 15th, so on the 14th in the afternoon or so, I saw this interesting tweet pop up from his account saying that he had noticed a severe error in one of the models that's basically being used to control shutdown of the United States when we reopen. It estimates the number of deaths and the utilization and whatnot of healthcare resources. It's a model out of, I believe, the model out of the University of Washington, or it's at least one of the places. So I got in touch, and miraculously, again, because of the wonders of Twitter, we have him here to talk to us about what he noticed and kind of walk us through a little bit and explain to us what he found and what the significance of what he found was. So can you tell me how you noticed this?
Okay, well, I do systems modeling for other industries, primarily for the last 10 years for U.S. Navy projects. And so I always follow modeling efforts. And I became interested in looking at the methodologies that were being used for the models and to examine them at a deeper level than was being discussed on the television. So I was collecting data. I read the original paper from Imperial College. It was very influential. And I was looking at the model funded by the Gates Foundation, the IHME model. And I was also looking at some other models that are starting to publish. One had caught my eye from COVID analytics by the MIT Sloan Business School. In epidemiology, there's a type of model that's been developed through the years from something called the susceptible, exposed, recovered model. It's sort of like a predator-prey model. It's a set of differential equations derived to discuss how patients move between states, where the predator-prey predicts populations. Similarly, it predicts the populations of people in each of the states. And that had been extended to being susceptible, exposed, infected, recovered, and dead, and some other states. And those models, they're not rigorous in that they're not modeling the system they're actually based on, but they try to mimic some of the underlying relationships in the system. And when I looked at the model from the University of Washington, I recognized the functions they were using because they were using a much more generalized modeling format. They weren't really using an epidemiology model for the death projection. So I'm not sure what they're using for their hospitalized and incubator, but for the death projection has become a pretty important number. When the White House first exposed that it was following this model, that number was about 83,000. 1 or 2 days later, it rose to 93,000 because the governors hadn't closed their states down, and the model assumed that they would within 7 days. So every day was adding about 10,000 deaths. And then pretty quickly, all the governors did close their states down. So the model did do good there. But then within a few days, it started predicting 60,000, which seemed extremely unusual. And then I have a lot of friends in New York. I also have friends in Philly. So hello. And I actually do a lot of work at the Naval Yard in Philly, at the Naval Surface Warfare Center down there, Carteret and Philadelphia Division. So my friends in New York I was worried about, so I was tracking real closely the New York curves. And I had the concept of harbinger cities that were ahead of us on the curve, or harbinger countries that might predict the outcomes for New York. So I started becoming very interested in Italy and Spain. And I looked at the data coming out of China, but it looks like at some point in time they stopped collecting data and then reported it as if it was like a miracle cure. So I didn't really trust the numbers that China had posted. It's because it stopped too abruptly, and that's not really possible. It's possible that they just locked down so fast that the medical community lost track of what was going on because the government took such severe action. And then I was looking at I was looking at the curves for New York City, Italy, and Spain a lot, and I noticed. I think the first thing that caught my eye was that their prediction for Italy predicted that deaths were going to stop at 22,000, and they projected it with very narrow error bands. And it was obvious that the error bands were too tight. So I knew it was an anomaly. And then I looked at the daily rates for it, and I could see that what had happened is Italy had gone through the first part of the S curve to the inflection point and was slowing down, and you could see the bend after the inflection point. And from that point in time, the projected uncertainty of this model had narrowed dramatically. So it was thinking for the parameters, it was estimating that they were well known at that point in time. So piecing that together, I looked at the basis documents and found out that they were using generalized S-curve equations, and the two equations they're using are both symmetrical. And because of that, it was clear to me that they thought that the three parameters they estimated were well fit and well selected from just passing the inflection point. And they were predicting these abrupt downturns that were symmetrical to the upturns. So I tried to get the word out. I sent an email directly to the IHME and gave them a little bit of time, and I got no response from them. So I started posting on Twitter and trying to contact some other people. Through my contacts on the law enforcement case I follow, I was able to get Chris Hayes actually to retweet me, which normally I have, I think, maybe 1,200 followers, and I'm not sure how much Chris has, but I had 200,000 looks in the next half hour. So Chris has a lot of followers. So when he retweeted me, it got it out a lot further, and I was able to reach the MIT modeling group, and I had been reviewing their results too and had some issues with theirs, and they said they were aware of issues and not to use their numbers yet. But they're coming out with a model that also projects the rate of deaths and the over time. So I've been following that one too.
So basically, the idea is that the functions that they're using to estimate deaths assumes that the first part, the rise, is going to be equivalent to the decrement, the downslope.
Yeah.
And so, and you're saying that based on what Italy and Spain showed, that's clearly not the case.
Right. So if I gave you a Twitter thread that has a lot of good plots in it that we can look at, if you can pull that up.
Yeah.
It was in our direct message window.
Yep. Under the United States coronavirus update.
Yeah.
I found a severe error, and then you said because of the error in the model's formulation only predicts generalized growth curves. That one?
No, this was when I corrected some things that were said in my original post, or extended it really. I sent it in my direct message. It should say on 413, I found a severe error in the underlying assumption.
Yep. Yeah.
Okay. And then, so if we can look at the artwork in this thread, and I think it'll help lead us to a talk.
Okay. Let me share that screen.
Don't remember the cartoon, but
can you guys see this or no?
yeah, it's
Is it just the cartoon or am I on the wrong thing?
you probably need to. The cartoon's still coming up, and
You see the other part or no?
yeah, we see it, but you might want to maximize.
Yeah. Sorry, I just wanted to make sure I was on the right thing here. All right, there.
Okay, so there's 3 pieces of artwork, and don't click there. So click on that.
Mm-hmm.
So this is actually taken from their documentation on their model. So they're using they're fitting the data to 2 curves. This is a description of their curve fit algorithm that they're using to project deaths from prior death results. If you're not familiar with modeling, this page may sort of intimidate you.
Right.
But these are actually 2 pretty simple equations. The top one's called the generalized logistic equation, and it's used to project S-curves, so things that start at one level and end at another level and rise in some uniform way. There's some generalized S-curves that were developed. Originally, they were developed to study biological systems, and then they've been extended to be more flexible in how many different curve types they can fit. So they actually used the generalized logistic equation, but it's actually a fairly simple version of the generalized logistic equation. They also used the Gaussian error function. The version they're using has the integral in it, so it's actually a cumulative Gaussian error function. So we normally think of the Gaussian error function as being a bell curve, but the cumulative curve, if you think of it, is really an S-curve. So it's very similar actually in shape to the generalized logistic equation. So if we go to the next piece of artwork, here's an arrow there on the right side of the screen. So this is just looking at their equation in Excel and plotting it. The p-value varies the amount of growth you see in the curve. So if it's 100, you grow from 0 to 100. The beta value translates the inflection point in time. So it controls where it's going to step up. And the alpha value controls the rate of rise. But the only curves you can generate with this formula are symmetrical in the first and third quadrant. So the rate at which you develop to the inflection point is going to be mirrored in the rate at which you decelerate in the slowing down portion after the inflection point. All it can, it's if you're going to fit this to things, it's going to predict symmetrical curves. There's nothing else they can do about it without using a more complex equation. So so if we go to the next one, this is the cumulative form of the error function, and it's just an S-curve too. The standard form starts at -1 and goes to 1, but you can vary the magnitude of the step very similarly. And if you increase, there's some constants added to generalize it, so you can change the slope of it and the median point. So there's really, they're forcing a symmetrical S-curve on this data, and that's what their model's going to predict no matter what. So if we close out of here, it looks pretty complicated, but it's really not. Now, this next step, I'm explaining what the derivatives look like for these curves, which are the ones we're more familiar with. So for the generalized error function, what you can do is you can make bell curves of various shapes if you're looking at like your daily death rates. So they're going to force the cumulative death rates to follow the S-curve, which is the same thing as saying they're going to force the daily death rates to follow these bell curves. But but what's going to happen is when they fit their parameters, they're going to determine during the rising portion of the bell curve that they know all three parameters very accurately. And then they're going to predict that there's no uncertainty on the falling part of the bell curve. So they're actually not taking into account their real sources of error at all when they're projecting their error ranges. They're just looking at the goodness of fit of the parameters. And if they're uncertain about the fit of the parameters, they think there's a large error. And if they're certain of the fit of the parameters to the data they have, they're thinking they have it very accurately, but they're forgetting they've made this underlying assumption, which is faulty.
Can you speak a little bit, because I've heard, and again, I'm not in the field, complete neophyte here, but I've heard of a distinction between curve fitting models versus other mathematical models, to forecast events like this.
Yes.
So are we here about, this is a kind of curve fitting models where really they make an assumption about what the curve is going to be, and it seems that they made an assumption of symmetry, and then they adjust it based on the data as it comes?
Right. And for this curve, they're going to get a good, after the inflection point of the bell on the rising side,
Mm-hmm.
They know pretty accurately all three parameters for the curve fit. But the whole assumption that it's going to follow a symmetric bell curve is of course just something untrue.
Right, because with the controversy about whether models take into account or don't take into account mitigation efforts or changes in human behavior and all that stuff, a model like this would essentially be a very mechanical model, right? I mean, it would assume sort of a.
But it's based on what mitigation in Italy and mitigation in Spain, correct?
Well,
I mean,
they could have done that. And I think in some of their projections, they have taken the factors into account. For these depth curves, I don't see any evidence they're doing that as of yet.
but yeah.
I
mean,
will say there are forms of this equation that can rise at a different rate than they fall. There's a version of the logistic equation called Richard's equation that has another factor in it that can make the decay after the apex be slower. And if they had fit that, say, to Spain and Italy, and then decided to use that factor that causes the decay rate to be slower when they fit New York, they could say they were assuming the same mitigation steps as Spain and Italy. But they didn't do that. They've assumed this symmetrical curve. It's very clear in their results.
I see. So
go ahead.
But so I mean, basically, they have a bunch of data from Italy and Spain in terms of how debts going up on a daily basis, and then I guess by the time they put out these models, they had I guess I don't know exactly when they did, but they had that back end of the curve as well in terms of the data, correct? Or could the problem be that they just didn't have that back end of the curve, and so only with a certain amount of information they just went about assuming that the back end would look like the front?
Well, with these curve fitting models, until you have data for the back end, if you assume a form where some of the parameters only are fit on the back end, then you'd be just totally uncertain about those parameters until you had some data on the back end. I really think that's the situation they were in. This simplifying assumption pretty much invalidates their projections. I think it might project the time to the apex, but it doesn't project the back end. If we actually look at our harbinger cities, we're just starting to have clearer back end data, and even
Right.
Spain and Italy is only about a third of the way back to zero.
Right.
When
Go ahead.
when you look at different cities or different prior experiences, are they similar enough that then you can, or you average them, or I mean, because circumstances can be very different from one place to another.
Right. So this curve fitting exercise, I think you'd have to characterize those cities and make fairly gross analogies.
Mm-hmm.
The other model type that MIT's using the susceptible, exposed, infected, recovered and dead models, you can actually measure the underlying parameters from your data. So you can see people moving through all the states, and then you can actually model other effects with partitioning of the population. So you run a model for each age group, and you can take into account the age group. There's a identified quarantine case in the MIT model. So it actually models a lot more of the concepts behind the system, where this is just a totally black box, where you're saying the system is going to follow curves of a similar shape. Mm-hmm. I do think they can do a better job with this type of model if they made the curves have a slower decay after the apex. And I think I've got some charts that actually show the data from Spain and Italy, so we can look at them after we've talked about the modeling curves.
So
if you go to the next picture,
yep.
This just shows for the other function how its derivative is just a Bell too, but it's symmetrical.
Right, symmetrical. Oops, and those are the two things you had there. Next one is here.
Yeah, this is, so I'm having people are like seeing these functions and their eyes are sort of bending back in their head. So I figure everybody has put some points in Excel and fit a curve through it. Not everybody, but I mean, anybody who's had any scientific training. So sort of what they're doing is they have the set of data points like I'm showing here, and they're fitting a parabola through it. And it has excellent fit. You see my R squared here is 0.996, meaning that the values of the constants in the parabola are well selected to go represent these points. The problem is the points may have nothing to do with the parabola, so they're actually using the downward leg of this parabola to project the future. And there's nothing about the data that, like if this was the altitude of something shot out of, say, a t-shirt cannon, we might know that the trajectory ignoring air friction is a parabola. And then maybe fitting a parabola, it would actually be a blunted parabola with air friction. But fitting a parabola might make some sense because we know the trajectory should follow a parabola. But this of course there's no underlying physics known to think this is going to follow a cumulative error function or a logistic function.
Right. So I mean, I guess Spain and Italy tell us what the downward limb will look like, but I guess it's possible if maybe partial yet. You're right. It's not complete yet. But you know, if suppose one of these drugs that ends up not to be working did work, or there was some game changer in how we manage these patients, then it's possible that you could have a downward limb of that curve that, you know, looks even better. Correct? Meaning it's not symmetric, but either way, not symmetric. I mean, there's no reason to expect it to be symmetric. Is your point?
It'd be unlikely to be symmetric unless there was an underlying scientific reason for it.
It'd be a new law, the discovery of a new law.
Yeah. So
here's
the data that actually keyed me off that something was wrong. So this was they first put up predictions for Italy. I think the day I made this discovery. So I think it was the 12th or the 13th. It looks like this is data from April 12th. And you'll see that Italy had data going up to where it turns into a dashed line. So they were pretty much beyond their inflection point. And their line had followed a cumulative error function curve very well. So they thought that they had discovered the curve fit and were predicting that the deaths had to end almost immediately. I think within 1,000 deaths. And they were projecting this real narrow error range, which When I saw this, I knew it was wrong. There's actually many sources of uncertainty projecting forward. Now you could think you know this within 1 or 2,000 patients so this was one of the charts, and you can see that the projected curve that they are overlaying is a symmetrical S curve. The next plot is the same curve fit for Italy, and this also seemed to have this extremely optimistic and anomalous projection in it. So if we look at the projected part of the curve, the dotted line, they're projecting that it's going to go sweeping down and become zero and vanish very, very quickly. Now, why are they doing it? They're doing it because that's the way it rose. And they fit a symmetric curve. Mm-hmm. So if they had drawn their whole symmetric curve, you'll see that that shape actually fits the front side of the curve real well.
Right, right.
And
just to be clear, all these are IHME
yeah,
curves that you're showing. Yeah.
Yeah, this is captures directly off their website on that day. So what happened, eventually I broke through, I guess, and started getting some people, at least at the University of Washington, interested. And this was what you tweeted. So if we go to, actually, if we go to Professor, before we do that, let's look at my last chart. I think is the one, no, lower. I'm sorry, that one right there. So this was, so what I was doing was, this was New York's projection, and you can see that New York was just reaching what we hope is an apex at right around 800 deaths per day. I think their top day was 799, but Governor Cuomo was saying it looks like a plateau because I think they have had 4 or 5 days where it's been within 5% of 800. But this model was predicting that it was going to drop off real fast because it projects symmetrical S curves. Mm-hmm. So you can see it's a very optimistic drop off. So what I did was I took the results for Italy on daily deaths and I rescaled it. But for some reason, every time I generate this, it shifts a little bit. I'm not really sure why. So that 1,000 line should actually be stretched up a little bit and be over the 1K line. But you can see that the Italy after the apex curve is not decaying anywhere nearly as fastly as it rose. And all that for New York would represent additional deaths. Mm. So they had revised their estimate down from, I think, 24,000 to as low as 13,000. But it's all based on, I think it's when they passed the inflection point on the front side and thought they knew their parameters real well. And it's anomalous, unfortunately, for New York.
Okay, so
now if we had tried to fit a decay curve on the backside through the Italy data, which we can do with some other curve fit formulas, there's a factor for the logistic formula called nu. That's an exponent on the lower term that can make the rise rate be different than the fall rate. They could fit that through Italy, assume the same nu factor, use their same curve fit program, and project curves that have the same relative rise and fall rates as Italy. And I think it would do a lot better. And their code was online, so I was thinking about modifying it and sending it to them, but I haven't had a couple hours to look at it yet. So if we look, there's a lot of interesting stuff in Professor Bergstrom's post. Actually, he does an excellent. So he took sort of the position I was taking, but did a lot more development of charts for it, and gives a really nice explanation of the problem. But it's very much in agreement with what I had found.
Right, right. Are you surprised that why did it take an anonymous gorilla on Twitter to discover this. I mean, again, the problem is, when I see, we're both cardiologists, and when we see, we read the paper, we may read the paper, we may read a blurb of the paper, but we certainly, it doesn't have a lot of meaning to us when we see those equations. But I would assume other modelers would have this. Would be, this would be kind of speaking their language. So,
well, I'm a pretty smart person. I try to be humble, and I represent myself as a gorilla,
But you mentioned at the beginning that there's a distinction between standard epidemiological models and maybe a model like this one.
Yeah.
And why do you think this one was adopted here, and why does it have so much prominence, it seems, in terms of policymaker and all that?
Well, I think they were really the right one to market their results the best first. So they had state-by-state projections. They had a pretty well navigable website.
Is it an easier model to sort of make more confident projections with the standard epidemiological model? Would they require a lot more data to be able to show anything? Or
I think the standard epidemiological. Okay, I don't even want to try that word right now.
Epidemiological.
Yeah.
There you go.
The standard model is more of a, I would call it a kinetics model. It has concentrations of people in different states and first order rate constants to go between them. Mm-hmm. There's a lot of parameters to estimate for it. So this was actually a pretty simple thing to do the estimation. There's just, they're 3-parameter models. So it's not much hard. It's a lot like fitting a parabola. It's just the curves a slightly different shape. And actually the position of the inflection point and the total height of the thing are 2 of the parameters. So there's really only one parameter, is the rate of growth and at the inflection point. I think their model was very simplistic. I think the rest of their website, they did some pretty good programming on to, allow everybody to go there, see their state, see the cumulative United States. And I think that was attractive to people. Mm-hmm. Not that many people have projections out there that way. The MIT group's website is not all that nice yet, but the model they're developing, I think they developed with an epidemiologist, and they are actually in the Sloan Business School of Management. So, and they have a very smart professor, and I think they have 20 MIT grad students, so that's a lot of free horsepower. This University of Washington group, I think, had 3 grad students, and they weren't MIT grad students. So I don't know what the relative power of MIT versus the University of Washington is in a grad program, but I think it's greater than 1.
But the
in my experience,
the SIR, I think, Michelle, you're alluding. So the epidemiological models are would you agree, or I don't know if you know, are they primarily the SIR models that?
Well, the SIR model is a historical model that was developed a long time ago. And then I guess the general category is enhanced SIR models. The SEIRs, where they introduce an exposed state, an incubation phase, and a infected state. And then and they have death rates, and pretty much all of them are SEIR now, or enhanced SEIR. And for this problem, they were adding all sorts of features to predict how many ventilators would be used. So they had the percentage of people in each age group going to intensive care versus not needing intensive care, and going to hospitalized versus being able to be home quarantined. So I think the MIT model was more of that traditional model format extended for this case. And I think pretty much, the the professor and the grad students were probably working with the medical team to get the requirements, but the people are general business case modelers. So they put it together very fast. Their website is not as nice yet, but I think if the University of Washington's issues come out, I think people will definitely be looking for another model to look at.
So, but given that there's multiple, so there's, if I can be allowed to try to summarize, there's epidemiological models that are based on, percentage of the population susceptible, how infectious that the virus or the pathogen is,
Right.
what percentage of population recover. There's extended, there's also additional models that are a little more complicated that you just described, but are still kind of use that SIR model as the base.
Right.
Then there's of course just pure, a little more pure mathematical models that essentially look at data points that have come before us, so in this case Italy, Spain, and look to try to curve fit to those models. Now, of course, and so depending on the rate of, and so this is dependent on the rate of rise of deaths in Lombardy or in Italy or Milan, being assuming that that's going to be similar here, and also assuming that, well, if Italy's drop off in deaths is so and so, then even that's what New York should also potentially look like. Do you have a sense of which? Now, it seems like the mathematical models are the ones that are kind of holding sway at the moment, and that seems understandable because there's so many different things with the SIR model that make it very hard to say with any confidence that this is what's going to happen. Meaning, the infection, how infectious a virus is differs whether it's in Idaho or whether it's in New York City. What percentage of the population is susceptible? We don't even have a good idea about how prevalent this infection may have been, what percentage of people are recovered, et cetera. So there's a ton of assumptions that go into all the SIR modeling.
Right.
Do you think that for those reasons, the curve fitting exercises that essentially is what we're doing, do you think that those should have more sway for those reasons?
Okay, so if you look at the SEIR models, if you developed it totally from first principles and tried to estimate all your parameters from isolated experiments trying to measure these specific rates between transfers or groups, I think you'd be lucky if it predicted with an order of magnitude of anything. But that's not what they're doing. What they're doing is they have a massive number of parameters. Some they're estimating from results, and some they're curve fitting. So you can think of it as the system of ordinary differential equations is going to just generate a set of curves, and just to make the optimization of those parameters to fit the data reasonable, we're setting some of the parameters.
And so it's more of a hybrid approach.
Yeah, because there's just too many parameters. Like in physics, I mean, fortunately, like we have geniuses that went before and left us equations that actually work. So when we're estimating things, it's like the mass of an object, or its inertia, or friction. I mean, we're not estimating things that we don't have mechanistic equations for. So I mean, it'd be hard to build rockets or things if you were depending on empirical formulas. So that would be better, but here you really are in a position where you need some level of empirical analysis. I think the SEIR gives you a model that will behave in its underlying ways more like the real problem. And but you do need to develop a lot of the parameters through curve fitting, or it's very questionable if it'll generate a reasonable result. I think the curve fit, if we started seeing very similar characteristic curves out of these cities for these S curves, I think the curve fitting could be very useful too. I just think they need to account for the fact, it looks to me like the decay after the apex is much slower than the rise. If it's always a certain ratio of the rise, then that would be easy to model. And then,
but can you clarify something about on that note, on that point? Are these models now, that these curve fitting models like the IHME, are they essentially, once you reach the apex, are they pretty much set, or they can continue to curve fit and change?
it'll continue, but what it's still, actually, if you go to Dr. Bergstrom's paper, he shows how the curve fit changes each day as data comes in that doesn't fit it. So can you pull his,
Yeah.
there's a really nice, I hinted at it with my overlay, but what he does is really nice there, because he found a website where he could pull up what they predicted 3 days in a row as data points came in that didn't fit. So if you scroll toward the bottom, even further,
Here.
further yet, he's got, I mean, he went off.
That's a long thread.
Okay, so here it is. This one or the next one is.
So this is the.
I think,
he says the
I think there's a better one. Go lower where he actually shows the front end of the curves too, I think. Yeah, that one. So go to the one on 29.
Mm-hmm.
Pop that baby up. So what happens is early, so on March 25th, when it had only seen a portion of the rising, it projected that green one. And as it rose higher and higher, it started projecting, but you can see it always projects these symmetrical bell curves. And what it does is if the data doesn't fit on the back end, it's going to just make the apex taller, even though it doesn't fit the data at the apex.
I see. Right. Right. So retroactively, the fitting is going to look worse.
Right.
Retrospectively, yeah.
It's sort of like if we looked at my parabola example and the rest of the points kept going up, the parabola fit would stop being near any of the points at some point, so that it could keep the outlier points from having too big an error.
Right.
And that's what's happening here. And actually, the total deaths under their curve is larger than was observed, but they're saying that was because the data had random noise in it, was their explanation. If they looked at their residuals, though, they'd have systematic residuals. It would show them that their model wasn't a good model.
Right. Although, of course, what makes it hard is that all of a sudden the state decides to count, 12,000 more cases retroactively, and
yeah. So for the curve fit, what you have to do is estimate when those happened over time and try to correct your data set.
Right.
You might find 2 or 3 sets of assumptions that you can make that are all reasonable, and then you run those as sensitivity cases, so you see how much it affects the results of your model. I don't see any of these people estimating their errors in ways that capture all their sources of error, which is something we do much more rigorously in engineering.
How would you do it? Or how do you do it?
Well, you have to identify. So what they were saying, the people in Washington were saying the only error source they had was the uncertainty they had in the value of their fit parameters. But they missed the source of error that their curve doesn't describe their data. So one of the things I work with is inertial navigation systems corrected by GPS signals. So in that problem, you're updating your position estimate based on your inertial navigation feedback, but every once in a while you got a GPS point that tells you you're in a different place, and you have to decide how to correct it what's most believable. So you have to very rigorously look at the likelihood of errors from all your sources and weigh your data using a Kalman filter carefully. And what I'm seeing here is they really don't understand the sources of their error and their estimates at all. I think maybe Governor Cuomo understood it better when he said that they really don't know what's going to happen after the apex. It could plateau, it could go down precipitously, or it could decay somewhere in the middle. I suspect that the underlying behavior would be a slower decay.
Yeah.
Because you have all these cases of infected people who haven't resolved.
Yeah. The hope is that the doctors are not just passive observers in this, and as it happens with most novel diseases, the longer you go, the more you learn and the better you get at managing these people. So the optimistic hope is that hopefully we figure something out in terms of management that maybe the Italians and the Spaniards, we learn from their experiences and learn from our early experiences to figure it out. So that's the hope, at least.
Yeah, I think the medical community does a good job of that, especially in diseases that they fight rigorously when they occur, things like cancer and heart disease. Maybe not so well in something like development of diabetes, because it's you don't really have your hands in it as much. But
right. Well, sir, this has been really great. Thank you so much for being thoughtful enough to take a deeper look at this. It's really fantastic. You really
great intro and overview for us neophytes. Thank you.
Yeah,
it's good.
Really great.
I mean, they're really pretty simple equations. It's always, you get to a point where sometimes they just switch nomenclature, and it's like you feel like, what the hell are they talking about? And you don't really have the gumption to figure it out. But they really aren't doing any rocket science here.
Excellent. Good to know.
Pleasure meeting you guys.
Yeah, pleasure meeting you as well. Thanks again. Take care.
Bye-bye.